We're going to look at the properties that different substances have. So we'll start out by talking about forces and bonds, and then we'll build up to talking about properties that solid liquids gases have, but more specific for AP. And so this unit is a really long unit. It has a lot of information in it, and we'll start out with talking about something called intermolecular forces. So an intermolecular force is a force between atoms, ions, or molecules. These are not chemical bonds. And we almost always simplify these down to IMF. So instead of writing out intermolecular forces every time, I usually write IMF. It makes life go a lot faster. IMFs are not a chemical bond. They are not sharing electrons, transferring electrons. There's no sea of electrons. It is not a bond. It's just an attraction. But it's really important because this attraction tells us things like, is the substance going to have a high or low melting point or boiling point? Or is it going to be able to be attracted to other surfaces or not attracted to other surfaces? And so it's a pretty important property for us to understand different substances. There's actually 6 different types of IMFs. 3 are much more common. So London dispersion forces, we simplify it down to LDFs, dipole-dipole, hydrogen bonding, dipole-induced dipole, ion-induced dipole, and ion dipole. I mean, they all sound crazy. Like they have crazy names that we don't use in our daily language, but you'll get comfortable with these as we go through this lesson. So for these things, we are going to have to first decide if something is nonpolar or polar. We have talked about this before, but we want to talk about it again. So a polar bond is when we have one element that is more electronegative and it pulls the electrons closer to it. And when it does that, they take on partial charges. So I have an example of hydrogen to chlorine. Chlorine is more electronegative. And so we have that partial negative on chlorine and the partial positive on hydrogen. When that happens, there is what is called a dipole moment. Di meaning two, pole meaning charged in essence. So a dipole moment is caused by an asymmetrical distribution in a polar substance. When we show that, we use this dipole moment arrow down here where we point towards the more electronegative element. If the dipole moment is caused and it does not cancel, remember we talked about tug of war, if there's not equal and opposite forces pulling on me, then I'm going to shift and move in whichever direction the greater force is. And so we have polar molecules are caused by those dipole moments that do not cancel. So let's do some Lewis structures to be able to figure out if these things are polar or not polar as we're going through talking about these dipole moments. So we have CO2. Carbon has 4 valence electrons. Each oxygen has 6 valence electrons. So there is a total of 12 plus 4, which will give me 16. Let me get my pen on. So I have 16 electrons I got to do something with. Carbon's going to be my central atom. My oxygens are going to be on either end. This one ends up having a lonely electron down here, a lonely electron here, and 2 lonely electrons on carbon. So what happens is it takes 1 electron from oxygen, 1 from carbon. They make a double bond. 1 from oxygen, 1 from carbon. They make a double bond. And then we need to draw our dipole moments to see what kind of distribution of these bonds are. So carbon is less electronegative than oxygen. Oxygen is closer to the top right. And so the way that it's going to work is you're going to have electrons pulled this way. You're going to have electrons pulled this way. Since both of them are oxygen, they have the same electronegativity, so they're going to pull with the same amount of force. And so if I were carbon and I had something pulling this way and this way, opposite but equal forces, then I'm not going to move. So this would be considered a non-polar molecule. Even though it has polar bonds, it is a non-polar molecule. Again, we're going to start with Lewis diagrams, figuring out what type of if it's polar or nonpolar, and then we use that information to decide some other information that I'll teach you in just a minute. Let's do NH3. Nitrogen has 5 valence electrons. Each hydrogen has 1, so it's a total of 3. So I've got 8 electrons. So I'm going to put nitrogen in the middle. It's going to share its lonely electron with each hydrogen, and then it has an unshared pair on the top. Nitrogen is more electronegative, so that means all of these electrons are going to pull inward, not opposite directions, not equal in magnitude. They're equal in magnitude, but they're not in opposite directions. It's pulling all of them into it. So again, this is like if I had an ability to pull 3 ropes in towards me, I'm pulling with greater force. Nothing is opposing me. So if you were holding that end of the rope, you would pull closer to me. And so then this is going to be polar because it is not opposite and equal, and this is not a symmetrical shape. So intramolecular forces are chemical bonds. So that's going to be our ionic, covalent, and metallic. Intermolecular are between molecules, ions, and atoms. There's an overall force called van der Waals forces. You'll hear these sometimes. You'll read them in articles or hear that word listed. It actually makes up all the forces that are covalent bond forces. So these are going to be things that happen between molecules that are covalently bonded. So they're not a chemical bond, they're an attractive force. So van der Waals forces happen only in covalently bonded molecules. There's London dispersion forces, dipole-dipole force, and hydrogen bonding. Again, all these forces are used for covalent bonds when it's between nonmetals, metalloids only. These are the attractive forces between their molecules. A London dispersion force, which we're going to typically abbreviate to LDF, is the weakest of those 3 van der Waals forces. It's just caused by the fact that things bump into each other, and you can sort of think of molecules like an elastic ball or slime. Or those gooey eyeballs you can get at Halloween, the little toy ones you can get, when you splat those things against something, they morph and change their shape. One side flattens and the other sides bubble out. Well, that's what's happening. Molecules are doing that same thing. So when they bump into each other, what happens is it shifts around their distribution of electrons. And so this causes it to have this thing called a London dispersion force. It is not a strong force at all. It is a force of attraction between molecules, not a chemical bond. So all covalent bonds have these things called LDFs, whether it's polar or nonpolar. LDFs are considered to be temporary induced poles. They only happen when it bumps into something, and then it moves on, and you don't have to worry about it anymore. So let's show what this is going to look like if I was to ask you to draw and show it in London dispersion force. So we're going to do this for a diatomic element, for iodine. Each iodine has 7 valence electrons, so I've got 14 electrons I got to do something with. So in diatomic elements, they just share 1 pair, and they're done. I'm going to draw 2 molecules. Now, this is a nonpolar bond because if they have the same electronegativity, there's an equal sharing of electrons. The only time that polar bonds happen is whenever there's an unequal sharing of electrons. And in these, it is not going to be a polar bond. And so when you show the London dispersion force to show in between them, sometimes people draw circles around them to show that it's a single individual thing. And that's fine. You can do that. But a lot of times people don't. But what they do show for the bond is a dashed line. So this dashed line does not look the same as that chemical bond. So when you have this dashed line, and like I said, you could have something showing this is its electron field, this is its electron field. If they bumped into each other, the electrons would shift around. And that's what it means by being induced, is that it's being forced on it whenever they just naturally bump into each other. If these were gases, they'd be moving all over the place and just bump into each other naturally. So LDFs exist in both polar and nonpolar, but this is an example of a nonpolar bond. Nonpolar are going to only have LDFs. That's the only force a nonpolar molecule can have is LDF. The next one is dipole-dipole. It is the strongest van der Waals force. It's going to be in the middle, and it occurs when something has a permanent dipole because there are a polar molecule, because there's polar bonds within it. And so with these, the attraction is caused by the fact that they have opposite charges on the different ends of the atom. So let's do HCl for this one. So H has 1 valence electron, Cl has 7, so there's a total of 8 electrons. And so I'm going to draw this. So H is going to bond to chlorine. These are not the same elements, so we have to look and decide if their electronegativity difference is very large, and it is between hydrogen and chlorine. Chlorine is more electronegative, so there would be a dipole moment pulling this way, which makes it be a polar molecule. When this happens, chlorine takes on that partial negative because the electrons get closer to it, and hydrogen takes on the partial positive. So what happens is over here, I will have another HCl. It also has a dipole moment pulling this way. This one will be partial negative. This one will be partial positive. And if I want to put my little circles just showing that this is the area of distribution for electrons for this one's the distribution for this one, what's going to happen is this partial positive is going to be attracted to the partial negative. So the attractive force is going to be between this hydrogen, that chlorine. And it just does that over and over and over in a sample of matter, because there's not just 1 or 2 molecules, there are Avogadro's number molecules within a sample of matter, okay? So this would be considered a dipole-dipole, is because these always have those partial charges, and so anytime they're next to something else that also has a partial charge, it can be attracted. Now, this doesn't have to happen only among substances that are the same substance. We could pour in a different substance that's also polar, and it could be attracted to these other options as well, the partial positive, partial negative. The strongest of the van der Waals forces is hydrogen bonding. And it's a little confusing because they called it hydrogen bonding, but it's not a bond. It is an attraction between molecules. A lot of times people say this is the Superman version of the dipole-dipole. It only occurs if nitrogen, oxygen, or fluorine are directly bonded to hydrogen, hence the hydrogen part. Because the difference in electronegativity is so great between hydrogen, nitrogen, hydrogen, oxygen, and hydrogen fluorine, it makes it be that the hydrogen is always partially negative and the other ones are, the hydrogen's always partially positive and the other ones are always partially negative. If we were to rank these because of the electronegativity, an HF bond would be more polar than an HO bond than an HN bond. And that's just because of the trend for electronegativity, because it's increase up, increase across. This one is the furthest over to the right, then this one, and then this one is the furthest away from the right. Hydrogen bond is formed by the hydrogen of one molecule and the O, N, or F of the other molecule. So let's draw water and look at it from that perspective. So H2O is going to be 6 electrons for O, 2 for hydrogen because each has 1. So it's going to be 8 electrons. So I'm going to put oxygen in the middle. Now, we know now that that water is a bent molecule. I'm going to do it up here. So water does this, making it be bent. You do not have to draw the two-dimensional Lewis structure to match the shape, but they almost always do with water. They're almost always going to draw water like this. You don't have to. You can do it this way, but they're going to write it like this, and here's why. Because this way it's going to be harder to show the attractive forces between molecules versus this way. So these hydrogens are going to take on that partial positive, and this oxygen is going to take on the partial negative because the electrons are going to pull towards the oxygen. So they're pulling all of it in. There's nothing that is, it's not opposite and equal in magnitude. So this would be one molecule. And then what would happen is I would have another molecule of oxygen over here. And this would be my partial negative again. And this would be my partial positive. So the attractive force is going to happen from my oxygen to my hydrogen, because it says here, the hydrogen bond is formed from a hydrogen of one molecule and the O, N, or F of the other molecule. So this O is partially negative, this H is partially positive, and so those are going to be attracted. So again, down here, what would happen here is this H would be attracted to an O from another molecule of water, and it would just keep happening over and over and over and over. There's also dipole-induced dipole, which means that you have a polar molecule and a nonpolar molecule. So this is like if I had a mixture, if I had more than one substance, or even if I was talking about more than one gas within an environment or liquids. The polar molecule will temporarily make the nonpolar molecule have a dipole. Again, they bonk into each other. It shifts electrons. It makes it end up being polar for a hot second, and then they move on and go on their way. So this one is temporary and induced. It's only going to happen when they come into contact. It is between something polar and something nonpolar. Ion-induced dipole is something that we're going to deal with. This one's going to be between a nonpolar molecule and an ion. It can also be a polar molecule and an ion. And again, this is temporary. It happens when the ion is attracted to the partial positive, partial negative end of that nonpolar or polar molecule. If that molecule has been temporarily induced, it can happen, or it typically happens with a polar molecule where they bump into each other and the ion is attracted to it. Ion dipole. So this one, again, this one's an induced one between the nonpolar and the ion. It makes the ion makes the nonpolar molecule end up being induced. Ion dipole is different. This is a big deal, and it comes up a lot later on in the year. An ion dipole is between a polar molecule and an ion. So our polar molecule, when we're doing these problems, is water. And the ion is going to be some sort of ionic compound dissolved in water. So this force comes up a lot later on when we start talking about solutions and dissolving different substances within a solution. And what happens here is, again, if I have water, let's say that I'm using the ionic compound NaCl. So if I have water, water is going to be, this is going to be my partial positive. And this is going to be my partial negative. When I put NaCl into a solution, it separates out into each individual ion. So I'm going to have my Na positive one and my Cl negative one. So my Na is going to be attracted to my oxygens. So this is going to attract to my sodium ion. My H is going to be attracted to my Cl negative ion. And so these are going to have attractive forces to those different ions. And that is the end for this one. The last thing I need to talk about is the concept of polarizability. So we use polarizability to talk about which thing is going to be more likely to cause those induced forces. And in this case, it's about the ability of that electron to be changed. So polarizability is increased by the size of the cloud or the number of electrons. So when we're looking at these, if I was comparing two different things, trying to decide which one would have a greater dipole-induced dipole, I'm going to look at the size of the two molecules, and whichever one has larger either number of electrons or size of the cloud. Remember, when we're talking about size of the cloud, it depends on if we're talking about atoms or ions, what the trend is. The trend for atomic radius was decrease up, decrease across. Ionic is that your cations decrease in size and your anions increase in size. And so polarizability is going to be something that comes up as we're going through talking about which forces are stronger and why. We can use this as an explanation. The bigger atoms, more electrons are going to make a force become stronger.